Hi everyone, thanks for coming. As the title suggests, I won't be talking about the good surprises we had when we moved our Xing platform to Kubernetes. There is no doubt that Xing, actually choosing Kubernetes for the new platform was a good decision. But this is not what the talk is about. During this talk, I will mainly discuss the things we had to figure out ourselves or understand in order to operate Kubernetes properly, and also some bad surprises, limitations, and issues, some of which are still open. This talk is rather technical. I want you to understand also the underlying issues we had, not just throwing some parameters at you. That's why to differentiate the slides where there's a concrete takeaway, I added this small logo, this small thumbs up. So today's plan, we'll talk about 4 specific points we wish we wouldn't have spent so much time on. The first one is the Nginx ingress controller. It's what brings the HTTP traffic inside our cluster. The second one is container networking in general, but you will see it's more about Linux networking in reality. Then I'll mention how resource allocation and limiting works under Kubernetes. And we will finish with a few minutes talking about how stable Docker is. So, a short introduction for those who don't know. Xing is a work-oriented network. We have 16 million users, and we are mostly operating in German-speaking countries. And as of today, we are around 1,400 employees. Some projects I have been involved in lately. One of them, the first one, is the Xing development environment. It's basically for developers when they want to test a change against other applications. They go on a web interface, they type a name, and after a few minutes, they will have a small Xing version with about 180 applications connected to each other and the right dataset loaded. At the very beginning, there were not so many applications like Xing, so it was basically Vagrant running on laptops. Then it became bigger VM on VMware, and now this is also all running on Kubernetes. So when someone wants to spawn a test environment, it goes on a web interface, and this will trigger the generation of around 180 pods with all the applications connected to each other. So I mentioned Kubernetes. I was also part of the team that introduced Kubernetes and is operating the Kubernetes cluster at Xing. We also supported the migration. As of today, I think almost everything at Xing is running on Kubernetes, at least for the social network part. And finally, I started recently with the team, working with the team in the site reliability engineering project. This is about measuring how applications behave and having some insight where to put effort when there are problems with your application. When we brought Kubernetes, there were a lot of new metrics, a lot of new alerts, and sometimes it can be overwhelming. And with this project, we have a few service level indicators that represent the service we offer to our users. And based on this, we choose to react or not on some of the alerts. So I mentioned the Kubernetes cluster. We have actually 15 clusters. We are not using this approach where you give one team a cluster. We have bigger ones where everybody can come in. We have 15 clusters. They have various size from 8 to 150 worker nodes, from 300 to 15,000 pods. So the one with 50,000 pods cause different type of issue, obviously. The Xing social network, it's about 230 productive applications, and everything is running on-prem with Ubuntu and on VMware. Yeah, sorry for that. So there is another talk a colleague of mine, Yegor, gave some months ago. It's about how we build actually the Kubernetes-based platform at Xing. If you want to understand how we went from this big picture on the left, which is actually a small picture with code that is packaged and then run somewhere on the cluster, maybe I can do it even bigger. Okay. There's this talk, you can look it up online. It's named Kubernetes at Xing, what it takes to build a coherent development environment. Because getting a raw Kubernetes cluster is not enough in an enterprise. You also want to have CI/CD integration with security, with some configuration management, with load balancer. So yeah, have a look. Okay, so the first pain point, the Nginx ingress controller. So it's a small software that runs inside the cluster and that will, based on Kubernetes configuration, generate some Nginx configuration. And Nginx will then take care of load balancing the traffic between the application. An ingress resource looks like this. For example, here we want all the traffic for logging.xing.com to be redirected to the logging app. And the logging app, it's actually the name of a resource behind which you can find the IP of every single instance of this logging application. We had a legacy platform that was already performing very well, so we had to make sure the new Kubernetes platform was performing at least as good as the previous one. And this is why we had to check two main requirements. The first one was that no request would be lost under normal operation, meaning that if a sysadmin adds a node, deletes a node, reboots a node, make a kernel update patch or anything, it shouldn't impact production traffic, so you can do real live update. And the other one is that requests always have the chance to last at least 60 seconds. Between a user and the final application, there are a lot of components that come into play. And well, every time we want to update one of those components, we need to make sure it has at least 60 seconds to finish what it's doing. The production readiness outcome we made was not that great, disappointing actually. So we found some bugs in Nginx. There was a very old one. When you would test the configuration with Nginx, Nginx-C, actually when you do it, what Nginx does under the hood, it starts a web server, but in test mode it ignores the error. But it means, depending on your configuration, if it succeeds to bind to the socket, it will capture traffic, and you will lose production traffic. So this is an issue Nginx fixed. We found a few other ones in the controller itself, where it will not gracefully shut down, so breaking our requirement, or even answering with wrong response code. So we fixed all of that. It took a week, two maybe. But at the end, there are still some settings we need to set in our cluster in order to fulfill our requirements. The first one is related to network interrupts. So we have in our Kubernetes cluster VMs that have this Nginx ingress controller. They receive a lot of traffic. I think it's up to 100,000 requests per second maybe. And well, by default, our Ubuntu installation, all the network interrupts are processed by the first core. They are not distributed. Our hardware actually supports distributed interrupts between cores when you install a package named ERQ balance. So if you are using also an ingress controller with a lot of traffic, you might have a look at your core, if the load is distributed or not, and install this package. The second setting is about the ingress controller shutdown. By default on Kubernetes, when you stop a workload, it will be given 30 seconds to exit gracefully, and after that it will be killed. Obviously, we had to change it to 60 seconds. The way Nginx works, you have a master process that spawns worker processes, and when you ask Nginx to reload the configuration, what it does actually, it's not real live loading. It's spawning new worker processes with the new configuration, and it's tearing down the old one. You need to get rid of the old one, because at some point you will not have enough memory else, and by default, the Nginx controller would give 10 seconds to shut down, for the old Nginx worker to shut down. And we made this configurable, and obviously you probably want to change it to something higher. Else, after 10 seconds, any connection that is going through your software load balancer will be shut down. I can try. I rebooted my personal one last weekend and it's dead since, but okay, cool, beautiful. It's still flickering. Okay. Okay, let's go fast until it breaks. So the last parameter is related to the deployment sequence of pods on Kubernetes. So on Kubernetes, everything is asynchronous. I'm sorry for the blinking. I hope, yeah. When you do a deployment, there will be the deployment controller talking to the API and asking for the pod deletion to the API server. The API server will propagate this order to the kubelets. So the kubelet is the agent running on all the Kubernetes worker. And the kubelet will send a SIG term to your pod. Starting here, the pod is usually starting to stop listening on the socket and properly shut down. But in parallel, the API also notifies the endpoint controller about this deletion. So the endpoint resource that contains all the IPs for the logging app, for example, is updated and the pod is removed. And only when the endpoints are updated in Kubernetes, the Nginx ingress controller picks up this new configuration, generates, well, actually new configuration for Nginx and sends a reload signal. And this reload signal operation is actually rate limited to 1 every 3 seconds. So we have a huge race condition here. It's unlikely that when your pod is shutting down, it has already stopped getting traffic. That's why there's a little hack you need to add to your container on Kubernetes. Some know it, not everyone. It's a bit ugly, but basically it's sleeping for 4 seconds. If you ensure when your pod shut down that kubelet waits 4 seconds before sending a termination signal, while you give time to all the other components inside the cluster to eventually have updated and stop sending traffic. An additional note, I mentioned the configuration reloads a lot. With the newer version of Nginx, it's not happening that often, but we're still kind of stuck with 0.10 because at some point we wanted to upgrade. There were a lot of regression. We fixed them, waited for them to go upstream, found other one, and eventually the latest release that came with the minimal amount of patches we needed has so many new features and breaking changes that upgrading is quite a small project. So we will look at alternatives, Envoy, for example, or Traffic 2, which has been released recently. Okay, second main problem we had, or bad surprises, that's actually the ugly one while moving to Kubernetes, it's the container networking. So how you expose your application to the outside is a choice Kubernetes leaves to you. We choose Nginx, but there are other technology available. And the network layer in your Kubernetes cluster is also a choice that is left to you. There are many plugins available, and we choose to install one which is named Flannel. And we used it in a mode that is named host gateway mode because it's the easiest that exists. So for our first cluster, it would ensure we can easily debug any problem on the network level. Short overview how this networking works. If pod A tries to communicate with pod B, it will send a packet. Packet will get out of the container, reach the host. On the host, the node 1 knows that pod B is on node 2. It will simply forward the packet without modifying it or anything. And when the packet arrives on the network interface of the node 2, it's forwarded to pod B. Communication is done. It's beautiful. It's inter-cluster communication. When you do communication with workloads that are outside the cluster, sometimes it's a bit different. Okay, Slack connected. Okay, when you communicate with workloads outside the cluster, it's sometimes different because very often your pod IPs are not reachable, which means your data center or everything that is outside the cluster is not aware of the pod IP addresses and cannot directly communicate with it. And that's why in such cases, the Linux kernel has to perform an operation which is named source network address translation, or SNAT in short. Basically, when the packet reaches the network interface of the host, it switches the source IP, the true source IP, with the node IP, and that way the external server can answer back to the node, and then the node to the container. This is true with Flannel in the mode we use it. It's true with other network plugin. It's actually how it works with default Docker installation. If you install the package on a VM, you will also have SNAT activated for outgoing traffic. That's how it works under Linux. At that point in time, so I think we are 2 summers back, we had migrated a few Ruby applications like the activity stream of Xing. And the data science team were starting to move their highly concurrent Scala application inside the cluster. They immediately reported some timeouts, and the only hints we had, basically, was that they were Scala. That was the main difference with the other ones. And they were doing a lot of HTTP calls to 2 very specific addresses, which are the highly available endpoint we have in our data center, behind which every REST API is exposed. We collected some clue, did a debugging afternoon. We noted that the response time jumps, the timeouts were response time jumps and not random at all. They would last 1 second or 3 seconds. We did some TCP dump so that the packets would leave the container, but would never leave the host, actually. And since it's the SYN packets that would disappear, it makes sense with the first clue, because the retransmission on Linux has an exponential backoff, so 1, 2, 4, 8, 16, which means that the first timeout you might have, if 1 or 2 packets get dropped, it's 1 and 3 seconds. And we found a counter related to NAT operation that is named insertion failed, and that would be non-zero. And actually, every time we would see a timeout in the application, this counter would increase. I mentioned this statistic, this counter. It comes from Conntrack. Conntrack is a kernel module that keeps track of every connection, and especially network address translation that the kernel applies on packet. And the problem is that this is all stored in a table, and when you update the table, there can be race condition leading to an insertion failure. There is an insertion failure, the packet won't be translated properly, it will be dropped. This is so true not only for Kubernetes and Docker, but this is actually how network address translation work under Linux. So it's it's valid for any other kind of technology that relies on this. The race condition is the following. If you have multiple containers on a single host, and they connect at the same moment to the very same endpoint that is outside the VM, then one connection might be delayed because of the packet drop. We did some experiments, same moment, mean from 1 to 4 microseconds on a multi-core VM, which never happens with Ruby application, but happens quite often with Scala application. And for us, it meant from 2 to 4% error rate on data science application, basically. So that was an issue. We looked into the kernel, modified some function, and found some flags that were already existing that allow you to randomize some variable used for the network address translation. And those flags brought the error rate to 0. They were not configurable from Iptable, so we put some patches. We modified Flannel also, so the network plugin we were using. This is all, well, the workaround are out there now. They help, but they don't fix the issue completely, of course. The flag we added to Iptable is named random fully. You probably never have to deal with it, but if you have user reporting connection issues in your cluster, you might want to check this insert fail counter. If it's non-zero, you know there are some some collision probably happening during those network operation. If you use Calico or Flannel as a network layer for Kubernetes, you can make sure you have the latest version because they have this patch. But there is no real way to solve this, and the issue in Kubernetes is closed actually, because they say, well, it's the kernel, it's very complicated to solve, so we will ignore this issue and try to fix it in the kernel, but we don't want to track it anymore. The second mitigation you can put in place, and actually it's probably a good practice also, is to reuse connection. So we had the tendency to establish new connection every time we make an HTTP request. For HTTP, if you use keep alive, for example, you can lower the amount of new connection per second. And of course, this mitigates the issue, because this issue is only when you build the connection. When the connection is already there, you don't face this issue at all. And well, the third recommendation, actually it's a workaround. Since we couldn't get rid of this error, we decided to get rid of the SNAT operation at all. So we choose another network layer that interconnects the Kubernetes pods with our data center infrastructure. It means that any workload in the data center is able to talk directly to our workload. And this way we don't have this issue anymore. Sadly, that's not it, because how network address translation are done on Linux. It's the same for source network address translation when you connect to the outside, or DNAT, destination network address translation. I won't explain how this works. It's more or less the same. And DNAT is used to reach the DNS services in Kubernetes. So here, again, there is a very big issue with like 200 comments and people complaining about DNS timeouts. This is when, especially on some Alpine Docker images, parallel resolution is being triggered. In that case, there are two connections started at the very same moment. There is a collision, and one of both DNS query will fail. I think in the latest version on Kubernetes, they are trying to mitigate the issue by installing local DNS cache resolver on every node. Okay, that was our ugly part. Now I talk a bit about resource allocation and especially about memory. It was last year, so in the middle of the migration, let's say half of Xing had migrated. We were adding new nodes on the cluster almost every week. And one morning, one team reported their deployment from being stuck. It would not completely finish. Something was happening. We looked at the cluster and saw some nodes that were not ready, meaning they are not healthy for the Kubernetes cluster. Some were not answering to ping. Other one would answer, but you could not SSH into it. And all sorts of applications, well, were restarting. Messy morning. So the culprit was found very fast. A developer deployed a optimization, removing the limit clause in the MySQL statement that ended up by loading, I don't know, 1 million records maybe instead of 3. The C driver would allocate gigabyte of memory, gigabyte per second, basically. And after more or less a minute, the host would be completely overwhelmed and crash. We were surprised by the impact of a single misbehaving pod. So we looked a bit deeper how the memory management works under Kubernetes. Let's put the incident aside and have a look how a node looks like. So here we have a Kubernetes node with 48 gigabytes of memory. Part of it will be allocatable. So that's the amount of memory this node will announce to the cluster to be available to schedule workloads. When you define your pod, in this resource section, you define usually a memory request. That's how much you would like to have. And Kubernetes will find a matching pod for a matching node for your workload. In this example, our node is 12 gigabyte big, so it can fit here. Not an issue, it gets scheduled. And actually, since we have 40 gigabyte, we can even put 3 pods on this workload. The limit of pods you can put on a node is mostly limited by the amount of requests. So the sum of all memory requests of all pods cannot go below what's allocatable. On top of this allocatable memory zone, you have an eviction buffer. This is used for emergency by the kubelet, so this Kubernetes agent. If the memory is becoming low on the node, the kubelet will try some smart eviction. It will gracefully ask some workloads to move somewhere else. And since this Kubernetes agent has a lot of knowledge about the workloads that are running, like the priority, the QoS class, or even the type of workload there are, it's able to make a more or less wise list of who to ask to leave the host first. It's a bit slow to kick in. In this example, I say we have 5 gigabyte eviction buffer. At that time of the incident, we had maybe half a gigabyte, and it's way too slow since we were allocating gigabytes of memory every second. It means kubelet would have to do everything in half a second, and it's not that fast. On top, the last zone of memory on a Kubernetes node, it's reserved for the system. So usually not everything runs inside Kubernetes. You still have a log rotate, maybe a journal D, system D, I don't know, some ganglia processes that run outside. And you have to guess a bit how much memory they use to reserve space for them. We've seen we could set a request on container, but you can also set limits. Like in this example, we will limit the workload's memory to 12 gigabyte. How this is implemented, it uses a kernel feature, which is named control group. The control group, they organize processes into hierarchical groups, and on every node of this tree, you can put limits, constraints. If one or more processes try to allocate more memory than they are allowed on this branch, there will be an OOM event, and one of those will be killed. If we come back to our example, so here we have a container using 9 gigabyte with a limit of 12. If it's trying to use a bit more than 12, it will be OOM, and this is what I'll name the first level of OOM. It's a container OOM. So only processes inside the container might be killed. Everything that is outside will never be impacted. If you are out of luck and the process that gets killed is PID1, your process will stop and Kubernetes will restart the pod somewhere else. That's what's beautiful about Kubernetes. Usually when something is broken, you restart or you delete, it comes back somewhere else and might even be working. So if we come back to our pods from the previous example where there's no limit, or it's actually the same if there would be a super huge limit, they would behave the same. Our pods here use 12 gigabyte. Everything is fine. We have 36 gigabyte usage and 40 allocatable and even 48 in theory available on the node. The pod can use more memory. That's perfectly fine. We want to improve the memory consumption on the cluster. So if there is memory left, they can use it. But there is a limit in how much all the container together can grow. This limit is the kube pod memory limit. Kube pod is the C group where the kubelet puts everything it starts. And the memory limit here is of node allocatable and the eviction buffer, so 45 gigabyte. Which means that if you have a container that, well, first, if you have a container that tries to use more than the available allocatable memory, you are basically eating your eviction buffer. And in this case, you have kubelet that will enter into action and ask pod to leave the node to free up some memory. If they don't leave the node quickly enough, in this case, you will reach the limit of the C group, and as for the container, you will have an OOM event. But well, it's a bit more painful, let's say, in this situation, because it's not the container that tries to allocate memory that will get killed, but it's any of the container that was started by kubelet that might get killed. So you can end up with one process allocating more memory and your neighbor actually be killed because there is not enough memory available in kubepods. The last time of OOM that can happen is on the host. So remember I said there was some memory reserved for system daemon, OpenSSH, and so on. We guessed they would use 3 gigabytes. If they use 3 gigabytes, everything is fine. If they try to use more, 8 gigabytes actually, well, they break a bit all the calculation and guesses we did. And if out of luck, we have one pod that tries to use 17 gigabytes, which is perfectly fine for it, right? Because the container has no limits, so it's allowed to grow. The container is not, the sum of all container is not bigger than kubepod, so everybody is in its right, basically. But still, there is no memory left on the host. And in this case, you have the third level of OOM. You have a host OOM, and here it's free shooting. Any process on the node can be killed, probably not PID1, but almost everything can die. That's what happened to us. That's why we lose some SSH connection and so on. You can slightly tweak how the kernel OOM killer behaves, but well, you will be in trouble. So, how to avoid this? What can we do to improve the stability of our platform? Well, the first recommendation would be to run everything, almost everything you can under Kubernetes. First, because then Kubernetes is aware of the real usage, memory usage, CPU consumption of your workloads, but also because, well, for ops, they can use kubectl logs, kubectl exec. They can basically use the normal developer tooling to interact with those system components. Periodically, we do revisit the kubelet reserved memory. So since it's a guess, you always need to make sure it's actually, your guess is actually still more or less right. An easy way to do it is to say, I put this node out of the cluster, and I looked how much memory is used. If no workload is on it, you know that what's left is actually the base limit you need to reserve for your system. And the last one is to leave enough buffer, this eviction buffer, for the kubelet to smartly evict pods. In our case, we had 500 megabytes, which is way too slow for this kind of incident. In the example, I say we have 5 gigabytes. Actually, I think we have even more. 15% of the memory on the host is reserved for kubelet to perform workload balancing when there is not enough memory. One way to increase the stability when a single pod is becoming completely crazy, it's also to put limits. They are here for this, actually. So we have an admission controller. I don't know if everyone knows, but the admission controller, it's a kind of small plugin that will run an operation on any workload being scheduled on the cluster. And in our case, this plugin will always set a limit, a default limit, if there is none. And this limit is equal to 1.5 the request. So it leaves some buffer for the application to leak. Yeah, exactly. But we don't want our developers to worry that much if they have a leaky application, let's say a slowly leaky application. That's why we wrote a small controller. So a controller, again, is a small piece of software that interacts with Kubernetes inside the cluster. This controller is named SoftOM Evictor. It watches all the workloads in the cluster, and if the usage of one pod is above 95%, we kindly ask him to be rescheduled somewhere else. If it's because of a memory leak, it will probably restart somewhere else using only 10% of it, so everything is fine. Back to the incident. So the two reasons that made this morning a mess was that the broken pod were allocating so much memory that the soft eviction system of Kubernetes could not kick in. That's why we need to increase the buffers. And the system daemons were killed because the memory reservation was not good enough. We had written that when we created the first cluster maybe 2 or 3 years ago, and it was not matching the actual usage of system daemons anymore. Okay, still here. wonderful. This is the last part, Docker. Docker has always been a major pain for us. We only upgraded it when there are security issues, but we don't care at all about all the features that come with it, Swarm and so on. We just wish it would be a stable container runtime. The issue we had would be the daemon randomly freezing, container inspection hanging. So you do container docker inspect on a container. Don't know, it stays, it freezes for like 5 minutes. Containers stuck themselves. You cannot stop them, not restart them, not remove them. You don't know why. Or the Docker shime would be crashing. For those who don't know, the Docker shime, it's the last process that is still in the host namespace, but that holds all the processes inside the container. So it's the one process at the boundary between your container and the host system. And this would crash from time to time with, apparently no reason. It's not that true. One example where it crashes is when some developer tried to start a Chrome driver inside the container, allocating a lot of memory. It would get OOM killed, and Docker don't always like that. The symptoms for Kubernetes are almost always the same. The nodes are flapping between the ready and not ready state. You don't really know why, you just get alerts. And when you look in the kubelet logs, you see plague is not healthy. Plague is not healthy. So the initial solution we found might sound a bit hacky, but we introduced a patch version of dump init that would delay the container exit by 5 seconds. So it means basically in all the containers we have, or most of them, we have a modified PID1 that will ensure that if whatever command you execute is ending in less than 5 seconds, we sleep, just to give time to everything outside the container to realize that the container has been started, that it's running and everything. That helped us quite a lot for the first year, I would say. But as many more applications were joining the platform, it was not enough. And we were seeing again those unstable nodes. So I said the kubelet, this agent, was complaining about the plague not being healthy. At some point where we looked it up, we looked at the source code and everything, how it works. That's, by the way, a good point. The Kubernetes source code is very well documented. Everything is in it. So in doubt, sadly, you have to go there, but usually you find the answer. So the kubelet, plague stands for pod lifecycle event generator. It's a Go routine inside, so a sort of thread inside the kubelet that lists all the containers that are on the node every second. And for each container, it inspects it, and then it reconciles the state of the container with the cache state in the kubelet. Like, is the container running? Was it started? Is it stopped? The plague is not healthy if this whole loop takes more than 3 minutes. The thing is, with the way our Docker was misbehaving, a broken container in kubelet is inspected. A broken container is inspected twice by kubelet, always, because it inspects the container once, and then the one it couldn't inspect the round before. There is a timeout in Docker operation that is set to 2 minutes in the kubelet, which means that 2 timeouts 4 minutes, you are above this 3-minute healthiness delay, and your node is not ready. So the way it's built, if you have one container that is broken on a node, you will have your node always flagging between node ready and node ready and node not ready. The first change we did was to increase the responsiveness of kubelet. The default timeout of 3 minutes sounds huge. It's only applied to what is called short-lived operation, like starting a container, creating a container. That should be super fast. We are not talking about displaying the logs of a container or pulling in images. 2 minutes is way too long. We lowered it to 5 seconds. Of course, the number of the error rate increased, because then the kubelet is able to do more operation, but it made the cluster way stable. back to this problem where the node is flaky for 3 minutes, saying it's not ready. The problem is that if in this loop kubelet is stuck, tries to inspect a container, and other workloads are being stopped, well, kubelet will never learn about it because it's still waiting for the first one to answer, which means the whole cluster is completely unaware that one container might have stopped already 2 minutes ago. That's why I think it's crucial to lower this value to something more reasonable, like 5 seconds. Then we looked, that was already a good mitigation point, but we looked into those inspection timeouts, where they were coming from. And it turns out, weirdly enough, they are caused by containers that have no processes. So basically, you have the shime, but there's nothing below. So the container, in theory, should be stopped, but it's still there for whatever reason. Or container with only zombies. Something happened, PID1 disappeared, and you have only zombies that are not being ripped off. We found an easy solution for it, a container killer. So we have a small software running on every Kubernetes node we have at Xing, and it detects those kind of workloads, those kind of containers that are basically stuck, and it kills them just with kill 9. That worked great. We never had such problem after that. Nobody even complained, and I looked at it, it's still killing stuff from time to time. So it means those containers don't matter that much, actually. And what is interesting enough is that this container killer also provides some metrics. I don't know if you're aware of it, but the way Docker daemon works now, you have your command line tool that communicates with a Docker daemon tool. Docker communicates with containerd, and containerd then manages the container. And when we measure the availability of the Docker daemon alone or directly containerd, containerd has actually way less problem than the Docker daemon, even if they are shipped together and they are supposed to be part of the same package. So one of the upcoming projects for a cluster is to completely get rid of Docker and talk directly to containerd. It has been out there for 2 years, and we have been waited a few times for security patches to be applied to containerd and then to be integrated into Docker so we can roll them out. By removing Docker from the equation, well, we know we will be able to make those changes more quickly. There is more to talk about. For example, IPVS. IPVS is supposed to be a new it's a new backend to be used for the internal load balancing system of Kubernetes. It's always announced as being something wonderful because it brings a lot of performance improvement, but actually the way it's implemented, depending on how your cluster is built, it can be way slower. We still do need to feel an issue for it. I didn't talk about CPU throttling also, which is interesting. Well, there's a lot more to tell, but I think it's enough for today. So I hope I didn't break the mood with those sad surprises. And again, sorry for the blinking. I need to say we are quite happy with Kubernetes, actually. Now that everything is running on it, we are able to reach a level of automation, automation we were not able to reach before. The path from the code to production for developer is way faster. We built this Kubernetes platform with the goal of being able to roll out a new application, completely new application on production in less than an hour. And actually, if you ask a fast developer to initiate some Node.js application, or I don't know, he only has one pull request to be validated by us, and then it's on production. So I'm sure he can achieve it in 20 minutes. And that's it for this talk. If you have any question, feel free. Thank you for listening.
Thank you. So if there are any questions, please raise your hand and I will come over with the mic.
And if you don't have a question about this talk or a question about, in general, the platform we built, that's also fine. And if you don't have question at all, that's also fine.
Okay.
Okay, thanks again.
Thanks again.